Okay, let's get started. Go ahead and respond. All right, please settle down, you guys. All right, we'll go ahead and get started. Go ahead and respond to the online poll if you haven't done so, and we will take a look at today's lecture, which covers K-means clustering with kernels. So we'll see how all of this works. Okay, I hope this knits. Great. Okay, so this is what we'll take a look at. We're still looking at K-means clustering, except now we're going to use kernel functions. Okay, and so just we'll review K-means clustering. Okay, so again, K-means clustering and all clustering is an unsupervised method. So there's no true or target labels that you are trying to guess. You are just searching for structure. You're trying to group similar objects together and keep different objects different, I guess, okay? And so, so as far as K-means clustering goes, you first have to start off with how many clusters you want to search for, how many K clusters. Then you randomly assign your points to each cluster. And then the next two steps are iterative, okay? Once all values have been assigned to a cluster, you calculate the centroids of the values in each cluster, and then you reassign values to clusters by associating values to the nearest centroid, okay? And then you go back and forth. So once they've been reassigned, you calculate the new centroids, then you reassign values, calculate new centroids, reassign values, and you keep doing this until everything converges. Okay? And so just kind of a few pictures of how this goes. Here's some data that, and we're going to search for 3 clusters in this data. Okay? And I start off with random assignments, black, red, and green. And then when we search for the centroids, okay, of each of these things, because they're random, they all end up very similar, but not exactly the same, okay? And because they're not exactly the same, there's going to be different distances. And so we're going to associate pretty much all of these points will be closest to the black one, and then pretty much all of these will be closest to the red. And there's only a few that are closer to the green point than either of the other 2 points. So after reassignment, we get this. Yeah, question?
Would it also work instead of assigning every point a color, just randomly pick 3 points as the means already?
Yes. Yeah. So if you look up K-means clustering, there's a few algorithms, and one will be rather than randomly assigning points to clusters, just pick 3 arbitrary points as kind of your initial clusters, and then go from there. So that's a perfectly valid method of initialization. Yeah. Okay, so we assign points like this, and then they get reassigned to their centroids, and then we reassign points, the centroids are recalculated, we reassign points, the centroids are recalculated, we reassign points, the centroids are recalculated, and then we reassign points, the centroids are recalculated, and then when we reassign points, there are no changes, okay? So, and so that means we have converged, all right? So, I think it's kind of neat, okay? So, reassign points, recalculate centroids, and then we reach convergence, okay? There's only, like, I think, just a couple points that get reassigned here, and then it works. Okay, so K-means clustering works real well for data that looks like this, okay? Where you're kind of kind of on the same scale, and Euclidean distance is really a good measure of similarity, okay? But it fails when Euclidean distance is not the best measure of similarity. And so for that, we're going to use a kernel function, and we'll do kernelized K-means clustering, okay? And so just to review, we've seen kernel functions before, and that was in our discussion of support vector machines. Except I didn't write all of the notes, so they weren't as pretty. And so anyway, here is this is what a kernel function is. It's basically the inner product or the dot product between two vectors after vectors have been transformed by some kind of function phi. Okay, and so so the kernel of some vector a and some vector xb, xa and xb, is going to be the inner product of phi applied to xa and phi applied to xb. Okay, if the phi function is the identity function, meaning it doesn't do any kind of transformation to it, then you get what's called the linear kernel, which is basically just the inner product, okay, or the dot product of xa and xb. Okay, so you can either do xa transpose xb or xa dot xb, and you know those are the same thing. Okay, so you get so in the linear kernel, phi is the identity function. Okay, but then we have other kernels, and this is I think one that we saw when we talked about support vector machines is this one will transform x. This should be you know the fancy phi, I guess, from a two-dimensional vector into a three-dimensional vector. Okay, so if you apply phi to x, if x is x1 and x2, this will transform it into x1, x2, and then x1 squared plus x2 squared. Okay, and if we look up, if we ask, well, what is the inner product of this? Okay, then this becomes, if we've got xa and xb, this will be xa1, xa2, and then xa1 squared, and plus xa2 squared for kind of our first thing, dotted with the transformed vector of xb, xb1, xb2, and xb1 squared plus xb2 squared. Okay, and if we apply the dot product or the inner product of these things, we'll get xa1, xb1 plus xa2, xb2 plus, you know, the quantity xa1 squared plus xa2 squared times xb1 squared plus xb2 squared. Okay, so that's going to be the dot product, which can then just be simplified into xa dot xb plus the norm of xa squared and the norm of xb squared. Okay, so this thing xa1, xb1, xa2, xb2 is just the dot product of this and this. And so we don't actually, we can go directly from the kernel function and work with the kernels directly. We don't actually have to transform them into three-dimensional space and do the dot product. We can go directly to the kernel. Okay, there's, you know, other kernels. This is known as the polynomial kernel. Okay, and for this polynomial kernel, if we just do like a quadratic version where c is set to 0 and gamma is set to 2, the transformation function looks like this, and then the inner product of this is going to be you know, xa1 squared, xa2 squared, and then root 2 x1, x2, and then we do it to xb, xb1 squared, xb2 squared, and root 2 xb1, xb2. And then when we take the dot product, we get this and this and this, which can simplify to xa1, xb1 plus xa2, xb2 quantity squared, and that just ends up being kind of the dot product of xa and xb, or the inner product of xa and xb quantity squared. Okay, so again, this is just to emphasize that the kernel function is basically the inner product after you've applied some kind of transformation function. But it's not even necessary to apply the transformation function. And so, you know, the polynomial kernel, you can read more about it. And then there's the Gaussian kernel, also called the radial basis function kernel, which is also an inner product, but you throw it into an exponentiation function, okay? You raise e to this inner product, okay? And this one, we can't even, the transformation function actually exists in infinite dimensions, okay? And that's a weird thing to think about, because you know, this one we can kind of picture. It's in 3 dimensions. It transforms from 2D to 3D. This one transforms it from 2D into infinite dimensions, okay? And what it's actually doing mathematically, okay? And mathematically what it's doing is it's using kind of the Taylor expansion of the e to the x function, which, you know, is an infinite series, and it's doing the inner product there, okay? But we don't have to worry about actually transforming it. We can just take the inner product. And so we can use kernel functions to do k-means clustering, okay? Okay, yeah, this again is that all kernel functions are inner products. We don't even have to think about the transformation. And so because we've got the kernel function is the inner product, or the, you know, phi applied to xa transpose times phi applied to xb, okay? A kernel can be used as a substitute for basically any inner product. So if in the original space you see an inner product like this, xa transpose xb, you can replace it with the kernel, okay? Because basically we're just going to say, well, what would happen if we transformed xa and xb using some arbitrary function phi, which we don't even have to worry about. You know, we can pretend we've got this phi function and then just replace it with the kernel function equivalent, if that makes sense. So, so we're going to basically look for things that look like this in the original 2-dimensional space, and then we're going to just replace things that look like this with the kernel function. So what we're going to do is we're going to apply this to k-means clustering, okay? And in k-means clustering, the points get reassigned to whichever centroid is the closest, okay? So we've recalculated these centroids, and then we're going to reassign points to whichever centroid is the closest. So, you know, these points are closer to the green centroid than the red centroid, so in the next iteration, all of these points got reassigned to green, okay? And so the way we measure the distance to a centroid, okay, if we're looking at the squared distance of a centroid, is we're going to take the point xn, and then we're going to figure out what the centroid mu k is, okay? The centroid of cluster k is mu k, and the squared distance is going to be xn minus mu k transpose xn minus mu k, right? So this is going to be, you know, the squared distance from x to mu k, all right? And the way we calculate the centroid, okay, mu sub k, is that we take, you know, we basically take the mean of all of the points x that have been assigned to that cluster, okay? So znk is going to be 1 if xn belongs to, this should be zjk. If that point belongs to cluster k, this z value is a 1. And if it doesn't belong to the cluster, it's going to be 0, okay? And then so we basically sum up all of the points that belong to the cluster, and then we divide by nk, which is going to be how many points belong to the cluster. Okay, and that's going to give us the centroid. And I think we covered this on Monday, but it's good to just review it again and see it again. So, so the centroid of a cluster is this. All right, and so what I'm going to do is I'm going to just plug this in to the distance metric. So I'm going to have xn minus this quantity transpose xn minus this quantity here. Okay, and then we're going to go ahead and expand this out. Okay, so we've got this. I've plugged in xn. Okay, I've plugged in this thing right here in for mu k, and I've plugged it in also for mu k. I'm using different subscripts. The textbook uses m and r, so I'm sticking with that. Okay, and then and we expand this out. Okay, so we do first, and then kind of the outer and the inner. Okay, and so we get. I guess I did the inner and the outer here. And then the last will have basically this summation times this summation. Okay, so we're going to get kind of this double summation thing. Is that okay? And this thing, 1 over xn zmk xn transpose xm, and 1 over this and this, these I can combine because these are both exactly equal to basically mu sub k times xn, and I've left off the xn here. I've got to kind of fix that. But these two things, even though they've got different subscripts, they're referring to the same quantity. Okay, so the mu sub k over here uses subscript r, and this mu sub k over here uses the subscript m. So they're different quantities. We can combine them. These two we kind of have to keep separate because it's going to look at every combination of m and r, every separate kind of point. Okay, so if you've got like 10 points in the thing, it's going to match up, points 1 through 10 and points 1 through 10, and you'll have kind of 100 possible combinations of m and r here. Okay, but over here they're the same quantity and they can be combined. So this here. Okay, as messy as it is, don't lose sight of what we're doing, this is just an alternate formation or expression of the distance of some point to a centroid. Okay, so this crazy thing here is the expression of some xn to some centroid mu sub k, all right? Except we no longer have to worry about mu sub k. We just have a bunch of inner products of x. Okay, and the reason for that we would want to do something like that is now we've got the distances expressed as a bunch of inner products, and we're going to just replace all of these inner products with a kernel function. Okay, so this thing is this thing down here is exactly the same thing as this thing up here, except wherever you see xn transpose x something else, it's going to be the kernel applied to xn and xn. Here I've got xn transpose xm, it's the kernel applied to xn and xm. And here I've got xm transpose xr, and it's the kernel function applied to xm and xr. Okay? But other than that, it's exactly the same. And remember, the kernel function is basically the same thing, x transpose x, except we've transformed x into some higher dimensional space using a function phi. Okay? But I don't need to worry about what that function phi is if I'm going to use the kernel function. It's going to go ahead and just, the kernel function gives you the result without having to do the transformation into the higher dimensional space. And I know it's weird, okay? But it took me a while to get this, so I'm trying to figure out how best to explain it, okay? And so what I'll do is I'll illustrate this being applied to a data set, okay? And I'll show you that it works by transforming it into the higher dimensional space. I'll do the actual transformation, and then we'll apply it, and we'll see the distances and all of that. And then we'll also calculate this using the kernel directly, okay? Is that all right? So if we do kernelized K-means clustering, this is how it goes, okay? The first two steps are the same. Determine how many clusters K you're going to search for and randomly assign your data points to the clusters, okay? And then the next step is reassign values to clusters by associating values in the data set to the nearest centroid using the kernelized distance, okay? And then you repeat this step until convergence, all right? And the difference here is that, you know, in regular K-means clustering, you would have to recalculate the centroids and then you reassign the points, okay? Here, we're just reassigning points based on kernelized distance. The kernelized distance doesn't require us to figure out mu sub k. There's no mu sub k. It used to be the distance was how far is x from mu sub k, okay? But we've expanded this all out so that mu sub k is no longer in here, okay? Because the centroid, mu sub k, technically exists in this higher dimensional space. So if we don't know the transformation function, we're not going to be able to figure out what mu sub k is, all right? But that's okay. We don't have to worry about the transformed space because we've got the kernel function. We can use the kernel distance, and when we figure out the kernel distance, it's going to say this is the distance to centroid 1, and this is the distance to centroid 2. And you didn't even have to figure out exactly where centroid 1 and centroid 2 are. Yes, question?
So we can just do like the old algorithm that we had before with the linear function for the linear kernel?
Yes, yes. If you use the linear kernel, that would be regular old K-means clustering, okay? And technically, you don't even have to figure out where the centroids are, right? This function will figure out the distance to some centroid, even though, and it's such a weird concept, it's going to say, this is how far you are from the centroid, but you don't actually know the location of the centroid, okay? And it's like it's strange because in my three-dimensional thinking brain, I can only think of like how far am I from this point to this point because I know the location of the point, right? But what we're saying is that, you know, in some higher dimensional space between, you know, I've got like these 3 points, I'm going to project them into a higher dimensional space, and in that higher dimensional space there is some centroid, but I don't even know the coordinates of that centroid. However, I can calculate the distance to this mystery centroid, okay? And it's so bizarre, but mathematically it works out because we've expanded out the expression of where the centroid is located into a bunch of inner products. Is that okay? It's weird, I get it, okay? So I'm going to just start off with this very simple data set, and I'm going to show you what, I guess, mathematically it's technically doing, is that, so I'm going to start off with the data in 2 dimensions. I'm going to transform it into 3 dimensions, and you'll actually get to, because I'm transforming it into 3 dimensions, we can actually picture it, and then we'll talk about finding the centroid the regular old-fashioned way in 3 dimensions, finding the distance in 3 dimensions, and doing regular K-means clustering with Euclidean distance in 3 dimensions, okay? And then we get kind of the distance to the centroids and all of that. But then I'll do it again, this time without any transformations and just using the straight kernelized distance metric, and we'll see that we get the same numbers, okay? Which is, I think, rather amazing, okay? So here, this is my data. I've got 4 points, basically 0.1, 0.1, but in each of the 4 quadrants, okay? So I've got the positive, 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 negative, negative, positive, negative, negative, and negative, positive, right? So I've got 0.11 in all 4 quadrants and the 0.22, but in all 4 quadrants, okay? And so this is what our data looks like. We've got 0.1, 0.1, 0.1 in the 4 quadrants and then 0.2, 0.2 in the 4 quadrants, okay? And so if we did K-means clustering, this point and this point would never be put in the same cluster because they are really far from each other using Euclidean distance in 2 dimensions, right? But we would probably say these 4 points are more similar and these 4 points are more similar. So what we're going to do is we're going to project this into higher dimensional space, okay? And so I'm going to transform it using kind of our x1, x2, and x1 squared and x2 squared thing. So I apply this phi function, and this is what I get, okay? So the points x1, point 1, point 1 get transformed into 3 dimensions, and their coordinate is now point 1, and 0.02. And then all of these points over here that are 2 are, 2, 2, 8, okay? And here I randomly assign them to clusters 1 and 2, okay? So I've got 2 in cluster 1 and 2 in cluster 2, okay? And this is what it looks like in 3-dimensional space. Let me we can actually plot this in 3D with an interactive 3D thing. Okay. Oh, did this not work? Okay, and then we calculate the centroids. All right, sorry. Okay, so we calculate the centroids and we get this. And you can't really see here, but let me plot this in 3D here, and this brings up this. Okay, and so can you see these dots? Okay, so here's our 4 dots down at the bottom, and now we've projected them into 3-dimensional space, and so you can kind of see that the centroid of the red dots, which is here, here, and these two is over here, and the centroid of the blue dots, which are here, 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 and here, are over here. And so they get projected into something like this. Okay. And then so we're going to reassign. You know what? My initial assignments. I don't know what happened here. Set seed 2. Okay. Sorry, let me change my initial assignments just slightly here. Okay, sorry. So when I project this into, so sorry, I just fiddled around with the initial assignments because we had this symmetric problem here. Oops, okay. And so with the initial assignments, I've got this point, and this point are red, along with these 2 points on the bottom are red. And then these 2 points, there's only 3 points assigned to blue, and so the centroids end up looking something like this in 3-dimensional space. And then when we'll calculate the distance to each of those centroids, okay? Let me re-render all of this. I'm a little bit weirded out. Set seed. All right, let's try this again. Okay. So we'll calculate the centroids in 3D, which we see plotted here. Okay. So when we calculate, what's going on with my? Okay. So we calculate the centroids in 3D, and they look like this. So this dot is the centroid of the points. It just disappeared on me, but okay, they're in different locations. It's hard to see in this projection here, okay? And we can calculate the Euclidean distance. So this is one of the centroids, and here's the other centroid, right? So we just take, you know, this minus this squared, plus this minus this squared, plus this minus this squared, okay? And we get kind of the distances to that point, and then, you know, we do the same for the other, and we get, you know, the squared distance to the other point. So these are the distances to the center, and then based on this, we recalculate the assignments. We say, well, the distance to centroid A is smaller for these 4 points, so they're going to get reassigned to cluster 1, and the distance to centroid B is smaller for these points, so they get reassigned to cluster 2. Okay? And then when you do that, this is all on the same plane. These 4 points are on the same plane, and so is this point. It's in kind of the intersection of, it's in the middle here, which, am I able to plot this again? I'm not sure. Okay, and then so after reassigning the centroids, you know, this is what we get. Okay, so the centroid of these points are up here, and then the centroid of these points are down there, and they are clustered correctly now. Okay, in a way that makes sense. And then we recalculate these, and so here are the 2 centroids, and this is where we're located. Okay, so so anyway, notice this page, which has the distance to the centroids when we project them into 3-dimensional space, okay? So we had to transform our points into 3D, we calculate our centroids in 3D, and then we calculated the distance from each of our points to the centroids in 3D, and these are the distances that we got, okay? We're gonna do the same thing, except we're gonna just use this kernel function, okay? We're gonna use the distance metric, and this is the distance from some point n to the centroid of cluster K, but we're going to just, rather than projecting it into higher dimensional space and then calculating the centroid and then the distance to the centroid, we can calculate the distance to the centroid directly using the kernel function and using kind of these vectors z, which indicate whether the point is in a cluster or not. All right, and so so here I just start off with kind of our arbitrary assignments with some points belonging to cluster 1 and some points belonging to cluster 2, and then I'm going to do z, and I'm going to just say, is the assignment equal to 1? And if it is, you know, then we'll make it true, false, and we'll say as.integer or as numeric, so it becomes 0s and 1s. So we'll have 1s for ZA will equal 1 if it's in cluster 1, and ZB will equal 1 if it's in cluster 2. Okay, and that will play a role into, you know, these kind of sums here. Calculating this part requires kind of the kernel for every combination of point M and point R, okay? So I've just created this matrix called KE, and I'm just filling it in for M and R, okay? So I've got a loop inside a loop, which is not ideal, but I'm just doing exactly what we've got here, okay? So we're gonna do, you know, some point XM multiplied by XR plus, you know, the norm, norm squared plus norm squared, okay? And so that's gonna calculate the kernel function for all points M and R. And that way I can just kind of look up the coordinate, you know, whatever pair of coordinates here, okay? And so the distance metric, this is what we've got for all 8 points. And this quantity, the double sum, is a little bit messy, but I'm going to just do basically Z, okay, for A, you know, it's going to be ZA and ZM, ZA for R and something like that, and we get this. It can also be, you can also be a little bit creative and just do ZA times ZA transpose and do element-wise multiplication with the kernel and sum that up, and you get the same thing, okay? But you can calculate the double sum using this, which is also equivalent to doing this, okay? And you can kind of mess around to see how it works. So anyway, here is, we're going to do the distances to centroid A, which is going to be equal to k, the kernel of xn and n, minus 2 times the number of points in cluster A, times basically the sum of the kernel of xn to all the points. So we've got that, plus kind of this double summation thing, times 1 over there, okay? So if I apply this, using only the kernel functions, I never had to calculate the transformed values or the centroid in the transformed space. But if we look at the values that we have here, 7.98, 8.25, and 7.17, and we compare them back to this slide where we did the transformation, calculated the centroid in 3D, and calculated the distances there, we get these same values, okay? So we are able to reproduce this value, column of values, which is the distances to centroid A, without having to transform it into the higher dimensional space and calculating the centroids in the higher dimensional space. We can get those distances directly right here by just using this distance metric, okay? And again, I know it feels very strange because we're saying here's the distance to some point in some higher dimensional space, and we don't even know the coordinates of where this point is in the higher dimensional space, okay? But we're still able to get these distances. And these values, like 31.857 is the same value that we get back here, 31.857, okay? Not impressed, okay. All right, and I think it's pretty cool, all right? Or at least mind-boggling that this is possible, that we can get these distances, okay? So here I've got 23.26 and 23.104, okay? And again, if I go back to that slide, 23.26 and 23.104, okay? We're able to get these distances, even though in our second run, we never actually transformed any of the values. We never actually calculated the centroids, okay? Because we've expanded out the distance metric using kernel functions. Is that all right? And so now that we're able to get these distances directly, okay? So we just calculate the distances to centroid A and the distances to centroid B without having to do any transformations. We can just look at these and say, oh, well, these 4 points should belong to cluster 1, and these 4 points should belong to cluster 2. And then we're done, okay? Well, I mean, and then we go through and we recalculate the distance metrics and whatnot, and then we'll see that no assignments will change, and then we would have clustered these accordingly, okay? And so so we would cluster kind of the 4 points in the middle together, and then we would cluster the 4 outer points together using this kernel function. Is that all right? What's kind of at least conceptually what's happening, even though like mechanically it's strange, right? Because I don't think we're able to comprehend the idea of figuring out a distance when one of the points is unknown. Okay, but we're able to do it by knowing kind of the locations of the other points together. Okay, so here's an artificial example where I kind of just take it to extreme, and I've got these points in the middle, and I've got these points in this outer ring. And if I did regular old K-means clustering, okay, so K-means clustering uses Euclidean distance. It ends up partitioning it something like this. And if I did a different run, I'd probably get something different. But basically, these points up here and these points down here will never be in the same cluster because the Euclidean distance from these points up here and these points down here are very far away, okay? So the Euclidean distance is very far, and so the Euclidean distance says these two, this value down here and this value up here, they are very dissimilar, okay? So that's what ends up happening, okay? Well, I guess, well, these ones in the, I don't know. All right, so K-means clustering is not ideal for something like this, okay? But I can do something with kernel K-means, all right? And kind of the, here we're going to, I'm going to use a Gaussian kernel, which takes, 2 points with, and I'm going to, square that and multiply that by some factor gamma, and here my gamma is 1, okay? And I calculate this, the kernel distance for all possible points, okay? And then we just start off with some random assignments, okay? So I just said sample 1 and 2 randomly, okay? And so these are kind of the random points. And again, because the centroid, the transformed data exists in infinite dimensions and the centroid exists in infinite dimensions, I'm not able to plot the centroid. No centroid can be plotted in 2 dimensions here, okay? However, we are still able to use that distance metric and reassign points to a cluster, okay? And so, so this is kind of what it looks like. The code here is I figure out my how many points are that vector z, zeros and ones, for if it belongs to cluster 1 or if it belongs to cluster 2. I need to figure out the double sum in order to get the distances, and then to calculate the distances, I take the kernel, for every point, the kernel nn, and minus 2 times 2 over n sub k for that kernel, or for that cluster, times the sum plus 1 over n squared for the double sum. Okay, and I calculate the distances to centroid A and centroid B at the same time, and then we say the new assignment is whichever column has the smaller distance, right? So I combine the distances, I bind them together to make a columns, and then I just say which column is smaller, okay? And those will be my new assignments, right? And if all the new assignments are equal to the old assignments, we're going to say it has converged. Otherwise, we're going to say it hasn't converged, okay? And then so I start off with random things, and after one iteration, this is what I get, okay? Which I'm not quite sure what it has done, okay? But somehow it says these points are more similar to these points, or I guess are closer in this whatever higher dimension projected space to whatever centroid it is, okay? And again, we don't know where the location of the centroid is. It cannot be pictured in 2D. It exists in infinite dimensionality. And so I don't think our brains can even picture this, but this is what it has said, okay? After this, we recalculate, we're technically recalculating the centroids, but we're not, okay? We just say, okay, based on these, can we figure out the distance, each point's distance to basically the new location of the centroid, okay? And we do that, and we reassign points. So we reassign points based on the distance to the centroids, and it does this, okay? And we do this again, and it's, calculating the distance to the centroid, and eventually it gets to this point, and at the next iteration, it doesn't make any new assignments, and it has clustered our points correctly here, okay? At least in a way that makes sense to us, in that, the points in the middle are quite similar to each other, and the points in the outer ring are quite similar to each other. And I recognize this is a toy data set, but it's an interesting way to cluster points without having to use Euclidean distance directly. And it depends on projecting the data into a higher dimensional space, but you don't even have to do that transformation into the higher dimensional space directly, which I think is rather amazing, okay? And again, it comes down to our ability, and this is the weirdest thing, is that we're able to somehow calculate the distance of a point to some centroid, even though we don't know the location of the centroid, by using the by expanding out the inner products. Okay, are there any questions on this? Yes, question.
Is it ever a thing to project the coordinates of the centroid back into 2D or whatever dimension, or is it just like leave it?
So the thing is we don't even know the location of the centroid. Is the weird thing. Because we don't have an expression for the centroid as an inner product. Okay, the expression for the centroid is this. Okay, this is not an inner product. Okay, the expression of the centroid is, you know, the sum of the z's times x. Okay, and in the transformed space, this is technically going to be the sum of z times phi times x. Okay, but we don't have that phi transformation function, and so we can't calculate mu directly, right? And again, it's weird. We're not able to do things with the thing itself, but if we can express it as inner products, okay, as we did here, now we're able to calculate the distance. The distance is found using an inner product, and so we can transform that, or not transform that, but we can kernelize that. But this thing, we can't kernelize because this exists in the transformed space, and we don't necessarily know the transformation function. I've provided like a couple examples of transformation functions and their corresponding kernels, but something like the Gaussian kernel or the radial basis function kernel, which are kind of used interchangeably, the transformation function again is an infinite dimensional thing, which you know, we're not able to compute. So yeah, it's strange. Like I wish we could know where the centroid is and transform it back, but it just doesn't exist. But because we've expressed it as inner products, we can use these kernel functions. Okay. All right. We'll end here, and we'll see you guys on Friday.